Hello everyone. This video for Monday, April 13th is going to focus on the molecular nature of dissolving, what affects the energy of dissolving, and reviewing the equilibrium between a solid salt and its dissolved ions. So we've talked about some of these things last semester, and I just wanted to connect equilibrium more to energy. So that's what we're going to do, and we're going to use the equilibrium of solid salts to kind of focus that discussion, thinking about the nature and the energy of dissolving things. So let's start with thinking about what happens at the interface of a solid ionic compound and water. So in this picture, we have here's kind of our surface of sodium chloride, the solid, interacting with the water molecules. Right? So the first thing that happens is that the ions start to interact with the dipole on the water molecule, right? We start to get solute-solvent interactions. And then the sodium and the chloride interactions have to be replaced by the dipole ion interactions. So it sounds a lot like intermolecular forces at work here. So we're overcoming one kind of intermolecular interaction and replacing it with a different kind of intermolecular interaction. So that's what's happening when something dissolves. So it's important to keep that in mind as we go forward, thinking about the equilibrium of that process. So when we have solute in a saturated solution, we say that it's in dynamic equilibrium with the undissolved solute. So here's kind of a picture of that going on, our undissolved solute. And this is sort of a time-lapse picture of, we can imagine this molecule kind of coming off the solid, this molecule coming off and going back. So there's always this dynamic flow of interacting within the solution and within the solid. So when we're thinking about this saturated solid, we imagine these particles, our molecules, or our ions, if it's an ionic solid, are in and out of solution and back in solid. So it's saturated, right? The solvent is full and cannot hold any more solute. And it's in dynamic equilibrium with a little bit of undissolved solute or solid. So we define this term molar solubility, S. That is the molar concentration of a saturated solution. So we can imagine that with a solution like our sodium chloride. So sodium chloride salt, when it dissolves, becomes sodium ions and chloride ions. And that's true of all ionic compounds. Or we can imagine something like sugar dissolving and having a saturated solution of sugar. So think of Kool-Aid with the sugary goo at the bottom is saturated, right? We've fixed as much sugar into that water as we possibly can. So you might remember or think about how it's important to distinguish between ionic versus non-ionic compounds, right? So our ionic compounds are often a metal and a non-metal combination, and a non-ionic compound tends to be all non-metals. So let's think about why something dissolves. And here's where I'd love to just ask you all and wait for your answer. Some hands will slowly, tentatively go up and they'll say, it's all about energy. Yeah, it's all about energy. So thinking about this picture of enthalpy and what's going on, so we've got our separate solute and solvent, so we have to break apart our solute, right? We have to separate the solute, separate our solid, whether that's separating the ions or separating two sugar molecules that are attracted to each other. And we also have to make holes in the water or our solvent or formation of cavities so we have a place to put those solvent molecules. Both of those steps require energy. Once we start interacting, right, our solute with our solvent whole, we get a decrease in energy once those cavities are occupied by solute. So essentially what's happening is that our solute-solute interactions are replaced by solute-solvent interactions, and our solvent-solvent interactions are replaced by solute-solvent interactions. So this tends to work best if we can mimic those interactions that are already present in the solute or already present in the solvent. So you may have heard this rule as like dissolves like. So it's really about if those interactions are similar in the solution as they were in the solid and in the solvent, then things tend to dissolve. So for example, we've got sulfur here in water, nonpolar solid in a polar solvent. It doesn't dissolve very well. The sulfur, however, does dissolve in carbon disulfide, which is also nonpolar. So similar interactions in the solvent and solute, so it does dissolve. So now let's switch gears a bit and think about gases dissolving in liquids and thinking about those molar solubilities of oxygen, nitrogen, and helium gas as a function of partial pressure. So we've got this graph here that's got molar solubility in moles per liter as a function of partial pressure. So the fact that we've got straight lines show a couple of things. First, the solubility of the gas is directly proportional to its partial pressure, right? We increase the partial pressure, the solubility goes up. And that's true for all three of our gases. And in general, it's true for all gases. If we increase the concentration, for example, of carbon dioxide in the atmosphere, we are going to push the concentration of carbon dioxide, the molar solubility in the oceans, higher. So this phenomenon was first observed by William Henry back in 1801. So the law that describes this is called Henry's Law, after William Henry. And we have the concentration of our gas is equal to Henry's Law constant, K sub H, times the partial pressure of that gas. So let's see how we can use that and how that varies with temperature. Right? So we mentioned that as we increase the partial pressure, it goes up. So what happens when we change the temperature? So here we've got the solubility of a bunch of different gases as a function of temperature, increasing temperature. And we see that for all of them, as we increase temperature, the solubility tends to go down. For helium, it kind of stays the same, but for most of them, it's going down. We can see evidence of this in a couple of ways. So first, we've got this glass of water. So if you've ever noticed, if you have a cold glass of water and you allow it to warm up to room temperature, you always get these little air bubbles on the inside of your glass. That's because our chilled water is warm to room temperature and the solubility of that dissolved air decreases, so it has to come out of solution. We can also see this, unfortunately, with large-scale fish kills and thermal pollution of lakes and rivers changes the amount of dissolved oxygen in natural waters, decreasing it, so there's not enough oxygen for the fish to survive, so they all die at once. So let's go back to thinking about how we can use Henry's Law constants to answer questions and solve problems. So our first problem is verifying the concentration of oxygen gas in lake water to sustain aquatic life. So what is required is 1.3 times 10 to the negative 4 moles per liter. We want to verify that that's what we have. So in general, at sea level, the partial pressure of oxygen is 0.21 atmospheres. So we're going to use Henry's Law. Concentration of the gas is Henry's Law constant times the partial pressure of the gas. So here in this table from the textbook, we've got Henry Law constants for several gases in water at 20 degrees. So we see that it varies depending on the gas. It also depends on the temperature of the solvent and which solvent it's being dissolved in. So we've got water at 20 degrees. So that's what we're going to use. So we have for oxygen, the Henry's Law constant is 1.3 times 10 to the negative third times a partial pressure of 0.21 atmospheres. So we find in general at that pressure, partial pressure of oxygen, we have 2.7 times 10 to the negative fourth moles per liter, sufficient concentration of oxygen for fish and other aquatic life to survive. Let's do another question. So in this example, calculate the amount in moles of carbon dioxide that will dissolve in enough water to form 900 milliliters of solution at 20 degrees Celsius if the partial pressure of carbon dioxide is 1 atmosphere. So we're really pushing a lot of carbon dioxide into our 900 milliliters of solution. Oh, I wish we could do this together and I could just put up this A and B and you guys could take a moment, calculate this, hold up your signs, and I could look out over the room and see you guys, and we could figure this out. Unfortunately, we can't do that on a video, but what you can do is pause the video, take a minute, calculate what you think it is, jot down if you think it's A or B, and then go through the answer. So pause the video, and now we can check our work. Right? So we're going to use Henry's law. We've got Henry's law constant of 3.5 times 10 to the negative 2 for carbon dioxide at 1 atmosphere. So the concentration in our 900 milliliters is 3.5 times 10 to the negative 2. But that is not the number of moles, right? To get the number of moles, we have to multiply that concentration by the volume in liters, 0.9 liters. So we will get 0.0315 moles of carbon dioxide, or answer B. So I want to go back to thinking about this effect of temperature on whether or not things dissolve. So what do you think is going to happen if you increase the temperature? And again, I'd love it if you guys answer this question rather than me talking to the computer. But what we're going to say here is it might be that you think if you increase the temperature, things dissolve more, but that isn't necessarily the case. Most things dissolve more quickly at higher temperatures, but that doesn't mean that more dissolves. Right? So increasing the temperature doesn't necessarily mean that it's more soluble, it just gets to the equilibrium solubility faster. As we've already noticed, for gases, if we increase the temperature, things are less soluble. Right? For solids, this effect is variable. It depends on the solid. Here's a quick look at a table of some solids, right? So not a table, a graph. So we've got solubility as a function of temperature, and we see that for some things it increases and for some things it decreases for the lithium carbonate. For some things it's funky and increases and then decreases. So it really depends on the solid that's dissolving. So now I want to switch gears from Henry's law and gases dissolving to think more about solids dissolving and what's going on in terms of energy. So let's connect this back to our free energy changes that we've been talking about in the last unit, where our free energy change is really a measure of our overall change in entropy and enthalpy. Right? So we were connecting that to whether something was thermodynamically favorable, which we were calling spontaneous, or not thermodynamically favorable, which we were calling non-spontaneous. Right? So in general, if we're looking at this picture of not dissolved to dissolved, the disorder of our system is typically going to increase when a solid dissolves, right? We get an increase in disorder and entropy when something dissolves. The enthalpy change can be either positive or negative, and that depends on the salt or the compound that is dissolving. So when we're dissolving, our change in free energy really depends on the balance between the change in entropy and enthalpy of the solution and the temperature at which that happens. So that's what's going on with our energy. So we can think about that in terms of our energy potential, which we have seen this picture before, and I'm going to show it again and again. It's the picture that's in my mind all the time, where we've got the free energy on one axis and either the progress of a reaction or the concentration of our solute on the other. Right? So if we're thinking about this equilibrium situation, right? So we have already talked about how at equilibrium, the change in free energy is equal to 0. So that's the minimum of our graph. So that's when we have that saturated solution that is in equilibrium. Solid and dissolved ions or dissolved particles are in equilibrium. So if we have less than that in terms of concentration, they're going to dissolve because they want to go towards equilibrium. If we have more ions or more solid dissolved in solution temporarily, it's going to precipitate. So we have the saturated amount of ions in solution. So let's put this into context as we think about and review the idea of the solubility product, which is really just the equilibrium constant, K, for an equilibrium between a solid salt and its dissolved form. So we're going to focus on ions and salts. So for our example, I chose antimony sulfide because it's one of the least dissolvable things there is. So we can write first the equilibrium for what's going on. So if I've got a saturated solution of antimony sulfide, I'm going to have solid antimony sulfide in equilibrium with its dissolved ions. And so when antimony sulfide dissolves, I make 2 moles of antimony plus 3 ions and 3 moles of sulfide ions. That's how that works, right? So we can think about the mole to mole ratio. For every 1 mole of salt, I make 2 moles of antimony ions and 3 moles of sulfide ions. Then we can write the equilibrium constant, K. So it's always the same, right? Activity of products over reactants raised to their stoichiometric coefficients. For antimony sulfide, this simplifies, right, to the concentration of antimony ions squared times the concentration of sulfide ions cubed. And we put the little SP there to remind us that what we've got going on here is a solubility product, solid as the reactant, dissolved ions as the product. So one way we can measure the KSP is to measure the molar solubility. We mentioned that earlier in the video, that S. What is the concentration in moles per liter of the compound in a saturated solution? And we've already used this, figured this out in one way, right? We used the E cell to find that concentration. So in those concentration cells, we could use this to find what is the concentration based on the chemical potential, or the electric potential rather, which is really connected to chemical potential, to find our K value. Another way is if we're given the molar solubility. So for antimony sulfide, excuse me, the molar solubility is 9.85 times 10 to the negative 20th molar. Not very high concentration. So if we want to find the value for the solubility product, first we can find the concentration of antimony ions, which would be 2 times this solubility, and the concentration of the sulfide ions, which would be 3 times this concentration, since there's a 2 to 1 mole ratio and a 3 to 1 mole ratio when it dissolves. We can put those values into our expression for K, right? So concentration of antimony ions squared times concentration of sulfide ions cubed. We multiply this out, we get 1.0 times 10 to the negative 93rd. So a very, very small value for the K, which means antimony sulfide really doesn't want to dissolve very much. So let's go through a couple of examples of how we can use this idea of solubility product, or the equilibrium constant, to answer some questions. So first of all, we can do another example like this one. The molar solubility of sulfur 1 chromate is 6.5 times 10 to the negative 5th moles per liter. Let's determine the value of the KSP. So this is analogous to what we just did with this antimony sulfide. So first we need to write that equation, our solid dissolving into its ions, right? So silver plus 1 ions, and chromate must be minus 2 since there's 2 sulfide ions, 2 silver ions. So the expression for K is then the silver concentration squared times the concentration of chromate ions. So we've got the solubility of the silver chromate compound is 6.5 times 10 to the negative 5th molar. And the silver ion concentration is going to be 2 times that, since it's a 2 to 1 mole ratio. And the chromate ion will be equal to that molar solubility, since it's a 1 to 1 mole ratio. Plugging those values in to our expression for KSP, we find, right, 2 times that 6.5 times 10 to the negative 5th squared times 6.5 times 10 to the negative 5th. We get 1.1 times 10 to the negative 12th is our value for KSP for the silver chromate. in this next example, we're going to find the molar solubility from the KSP. So we're going to go at it backwards. So if the solubility product for lead to fluoride is 3.7 times 10 to the negative 8, what's the concentration of lead in the solution? What's the concentration of fluoride in the solution? What's the concentration of lead fluoride in the solution? So just as before, we're going to write the balanced chemical equation. Lead fluoride solid dissolves into lead ions and 2 fluoride ions. The KSP is equal to the concentration of lead times the concentration of fluoride squared. So our question is, what is this overall concentration, the molar solubility? Since the concentration of lead, right, is going to be the same, it's a 1-to-1 mole ratio, and the concentration of fluoride is going to be 2 times that because it's a 2-to-1 mole ratio. If we substitute into the KSP expression, lead concentration times fluoride concentration squared, right? So we know what the KSP is in this situation. It's 3.7 times 10 to the negative 8 molar. That is equal to the concentration of lead, or S, times the concentration of fluoride, which would be 2S squared. So our 3.7 times 10 to the negative 8 is equal to 4S cubed if we multiply this out. So we solve for S. S, our molar solubility, is 0.0021 molar. And that is our molar solubility of lead fluoride. So I wanted to take a moment to look at a bunch of KSP values and think about if we can use this KSP values as a guide to relative solubility. The answer to that question is a qualified yes. We can only if we are comparing compounds that contain the same total number of ions. For example, it's difficult to compare calcium carbonate to calcium fluoride. Calcium carbonate breaks apart into 2 ions, calcium and carbonate, and calcium fluoride breaks apart into 3 ions, 1 calcium ion and 2 fluoride ions. So comparing these is not such a great idea. We could compare copper bromide, copper chloride, copper iodide, because all 3 of those break apart into 2 ions, and then we can see that there is a trend, a periodic trend there, that the copper chloride is more soluble than the bromide, which is more soluble than the iodide. So this is a short table of KSP values. There are more K values in Appendix 5. So there's KAs and KBs and KSPs in that table in the back of your book in Appendix number 5. If you're looking for those, say when you're doing smart work problems, you will find values for KSP in Appendix 5. So I want to come back to this question of will or will not a solid form? So we want to think about K versus Q. So this kind of helps us think about remembering equilibrium, right? So Q is just a special form of K, right? So when the solution is saturated and we are at equilibrium, the value of the quotient Q is equal to the value of the equilibrium constant K. If the solution is momentarily supersaturated, we've managed to get a higher value for the quotient than the K. That means we have more ions in solution than what will fit. They will precipitate until we get back to the equilibrium amount the solution is saturated. If we are in the situation where the solution is not saturated, if we're putting in solid in a concentration that is lower than the equilibrium concentration, the solid will dissolve. So let's work through one more example. Does a precipitate of barium fluoride form when we mix 100 milliliters of 1 times 10 to the negative 3 molar barium nitrate with 200 milliliters of 1 times 10 to the negative 3 molar potassium fluoride? Given that the KSP of barium fluoride is 1.7 times 10 to the negative 6. So our first step here is to think about what's going on. What we want to do is find the QSP. What's the Q for barium fluoride in these conditions? And then we can compare it to the KSP of barium fluoride, that saturated equilibrium point of 1.7 times 10 to the negative 6th. So we need to find the concentrations of barium and the concentrations of fluoride for this situation if I mix 100 milliliters of this with 200 milliliters of this. Right? So for barium, we can find the number of moles, right, for anything. Barium nitrate is going to break apart into barium ions and 2 moles of nitrate ions. So the concentration of barium ion is going to be 0.001 molar times the volume in liters, in this case 0.1 liters. So we've got 0.0001 moles of barium in a 100 plus 200, 300 milliliter total. So the concentration of barium ions is going to be 0.00033 molar in this situation. For fluorine, we find the number of moles of fluorine from what was added, right? 0.001 molar Kf, 200 milliliters or 0.2 liters. So we've added 0.0002 moles of fluorine ions in 300 milliliters total. So for fluoride ion, the concentration in this situation is 0.000667 molar. So if we substitute that into our expression for Q, the concentration of barium times the concentration of fluoride squared, we get 1.48 times 10 to the negative 10th, which is much smaller than 1.7 times 10 to the negative 6. So the ions will stay in solution and no solid will form. Hang with me, guys, one more slide. The common ion effect. So we want to think about what happens to solubility if we add some other ions. So the common ion effect is that we get a decrease in solubility caused by the addition of a common ion. So let me go back to our example. If I added in some, say, sodium fluoride, in addition to the potassium fluoride, or if I was mixing these instead of in water in sodium fluoride, I'd have extra fluoride ion that I'd have to account for here, and it would change the Q, so it would affect the solubility equilibrium of what's going on here. So that's what's going on with the common ion effect. Changes the solubility. So the question I have for you now is, what effect would pH have on solubility of ions? I'm pausing because I wish you could answer. Considerable if the ions are either weakly basic or weakly acidic. So let's consider calcium carbonate or marble. So calcium carbonate dissolves into calcium ions and carbonate ions. So if we think of, I don't know, say acid rain dissolving marble, why does that happen? Why is it that if the rain is more acidic, the marble dissolves faster? So let's think about these ions that are formed when calcium carbonate dissolves. So calcium ions and carbonate ions. So we may recognize that carbonate ion is a weak base. So when it is dissolved in water, it will set up an equilibrium with its conjugate acid, bicarbonate or hydrogen carbonate ion, and hydroxide ion. Right? It's weakly basic. It makes hydroxide ion in solution. So if I am increasing the pH of my solution, so it has a higher concentration of H plus or H3O plus, well, we've already seen if I've got OH minus and H plus, they combine to make water. Strong acid, strong base makes water. So essentially at higher pH, this is removed, right? My hydroxide is removed from solution. So if I'm removing this product, I'm going to shift the equilibrium of this reaction towards the product side. So I'm going to use up the carbonate ion. And if I'm shifting this equilibrium in this direction and I'm using up carbonate ion, then I'm also going to be shifting this solubility equilibrium towards products. So I'm increasing the solubility of the calcium carbonate due to the increase in acidity in the water. So it's Le Chatelier principle working. For more on this, you can look at the animation common ion effect in chapter 16. This is a link on the PowerPoint. You could also, if you want to, start activity 25 on Sakai. The final question of that activity is covered in the Wednesday video, so it won't be due till the end of the week. But you could go ahead and start that while this solubility stuff is fresh. That's it for now.